Hey everyone, today we're going to do a 3D building example in OpenSees Navigator. So first, we're going to construct a 3-story frame building. Set the OpenSees.exe path first. Now we're going to add some nodes. Insert the number of dimensions, which is 3 in this case, and the degrees of freedom, which is 6. Now we're going to enter the corresponding coordinates for each node. Now we also create 3 nodes where each node is located at the center of each story. Now we're going to define some elements. Now we're going to add nodal constraints and nodal masses. First, we're going to add the SP constraints. We're going to constrain all 4 points at the base for all 6 degrees of freedom. For the 3 points at the middle of each floor, we assign the constraints for a Z translation, rotation about the X and Y axes. Now we're going to add the MP constraints. We're going to add rigid diaphragm for all 3 floors.
Can you tell me the notes? I just turned off.
17, 5, 6, 7, 8. Master 18. Master diaphragm 2. Yeah. Yeah. 9, 10, 11, 12. Then master 19.
Just remember to turn off.
13, 14, 15, 16. Now we're going to assign nodal masses. We're going to assign masses to the 3 nodes in the middle. Now we are going to define uniaxial materials. We're going to first add a new concrete 01 material, and we create a core concrete material. We give it compressive strength of -5, strain at FPC of -0.005, crushing strength at -3.5, and strain at SPCU at -0.02. Now we're going to do the same thing and create cover concrete. And we give it compressive strength of -5, strain at FPC as -0.002, crushing strength as 0, and strain at SPCU as -0.006. Next, we're going to add a steel 01 section, and we name it rebar. Fy is 60, E modulus is 30,000, hardening ratio is 0.02, and we leave the rest. Lastly, we're going to create elastic torsion. So you choose an elastic material. We name it elastic torsion, and we input the modulus of elasticity. And we add it. Okay, now we're going to create line sections. We're going to add a fiber section named column. We're going to add a new patch, and we call it top cover concrete. And the material type is cover concrete. And the lower left corner is 6.5 and 9. Lower right corner is 6.5 and -9. Upper right corner is 9 and -9. Upper left corner is 9 and 9. And the number of fibers are 10 and 1 respectively. We're going to create another one called bottom cover concrete. The material type is cover concrete. Lower left corner is -9 and 9. Lower right corner is -9, -9. The upper right corner is -6.5 and -9. Upper left corner is -6.5 and 9. And the number of fibers are 10 and 1 respectively. I'm going to create the left cover concrete now. And the material type is cover concrete again. The lower left corner is -6.5 and 9. Lower right corner is -9 and 6.5. The upper right corner is 6.5, 6.5. The upper left corner is 6.5 and 9. The number of fibers are 1 and 8 respectively. And we're going to create the right cover concrete. And we have the material type as cover concrete. And the lower left corner is -6.5, -6.5. Lower right corner is -6.5 and -9. Upper right corner is 6.5, -9. Upper left corner is 6.5, -6.5. And the number of fibers are 1 and 8 respectively. Finally, we're going to add the core concrete. And the material type would be core concrete. The lower left corner is -6.5, 6.5. Lower right corner is -6.5, -6.5. Upper right corner is 6.5, -6.5. Upper left corner is 6.5, 6.5. The number of fibers are 10 and 10 respectively. Now we can add rebar layers. We define a straight layer for left rebar, and material type is rebar. Starting point is -6.5, 6.5. Ending point is 6.5, 6.5. And the number of bars is 3. And the area of the bar is 0.79. Now we're going to add the middle rebar. And the material type is rebar. Starting point is -6.5 and 0. Ending point is 6.5 and 0. Number of bars is 2. And the area of bars is 0.79. Finally, we're going to add the right rebar. Type is rebar. And the starting point is -6.5, -6.5. Ending point is 6.5, -6.5. And the number of bars is 3. And the area of the bar is 0.79. And we add the section. Next, we're going to create an aggregator section named aggregator column. And we're going to choose elastic torsion for the torsional input. And we create the existing section, which was column. And we add it. Next, we're going to add a beam, which is an elastic section. And with the following input. And we add the section. Now we're going to define line elements. We're going to create a column by adding an add force beam column element. And we name it column. The number of integration points is 4. And the section type is aggregator column. And we also create a beam by adding a force beam column element, and we call it beam. And the number of integration points is 3, and the section type is beam. And we add. Next, we're going to assign the element types. So we assign the column to all the column elements, and we assign beam to all the beam elements. Now we're going to define the time series. We add a new path file and name it tabs.fn. The time interval is 0.02 seconds, and we need to locate the file. The load factor is 386.4, which is also gravity. We add another path file and name it tabs.fp. The time interval is 0.02 seconds again, and we need to locate that file. And once again, the load factor is 386.4. Next, we're going to define the load patterns. The first one we'll define is gravity, which is a plane load pattern. And we keep the time series as linear default. Next, we're going to create the first earthquake load, which is tabs.fn. And we select tabs.fn for the time series type. And the direction of excitation is 1, which is the x direction. And we're going to create another earthquake load, which is tabs.fp. And we select tabs.fp from the time series type. And the direction of excitation is 2, which is also a y direction. Now we are going to assign nodal loads to the corners of each story. Make sure its load pattern is gravity, and so we're going to assign negative 130 kips of force for the FZ direction. And we add. And we're going to go to the display options to make sure we choose the loads. And we choose gravity and display, and we should see it in red. Next, we're going to assign geo transformations. We're going to insert all elements as linear transformations. Now we can go ahead and define some recorders. We're going to first modify the default shape recorder. Make sure all the nodes are selected and that we select displacement, velocity, and acceleration. Now you can also modify the eigenvector recorder. Make sure that all nodes are selected and the deformation is just the eigenvector. Now we create a new beam column element recorder, and we name it element force. We select all elements, and the deformations should be global and local resisting forces. Next, we're going to define the analysis options. We're going to create a new analysis option for gravity. So we name it gravity, and the analysis type is static. The constraint handler type should be transformation method, and integrator type should be load control. And the input should be 0.1 for the load increment. Number of iterations is 1. Minimum load increment is 0.1, and the maximum load increment is 0.1. And we go ahead and add that. And the solution algorithm type should be Newton. And we add. The convergence test type should be normal displacement increment. And we add that. And the DOF number type should be plane. And finally, we check sparse general. And we make sure that the partial pivoting is checked. And we add. And we add this analysis option. Next, we're going to modify the transient default. And we're going to have the analysis type as transient, the constraint handler as transformation method, and the integrator type as new mark. And add. The solution algorithm type should be Newton, and the convergence test type should be energy increment. And add. And the DOF number type should be plane, and the system of equation type should be sparse general, and we check the partial pivoting again. Next, we're going to modify the eigendefault. The analysis type should be eigen. The constraint handler type should be transformation method. The integrator type should be new mark. And we add. The solution algorithm type should be Newton. The convergence test type should be energy increment. And we add. And the DOF number type should be plane. And also the system of equation type should be sparse general. And we check the partial pivoting. After defining the analysis options, we can define the analysis cases. First, we're going to add a gravity case. We're going to name it gravity, and the load pattern should be gravity. The recorder should be default shape and element force. And the analysis option name should be gravity. And we'll set the load step as 10. Next, we're going to modify the eigen default case. Load pattern name should be none. The recorder should be eigenvector. The analysis option name should be eigendefault. And the number of eigenvalues should be 9. And we'll set the algorithm type as frequency generalized and the solver type as full gen LePac. And lastly, we're going to add the transient case. We're going to create a new case, name it transient, and we start from the previous case named gravity. The load pattern name should be tab as Fn and tab as Fp, and the recorder should be default shape and element force. The analysis option name should be transient default. We'll set the number of load steps to 2000 and the time increment as 0.02. And now we're going to set the damping parameters. So we keep it as damping parameter 01, and we are going to change the region defined by nodes and then node or element number to all, and we click calculate. The damping type should be stiffness proportional. The ith mode damping ratio should be 0.5. And the ith mode period should be 1.279. And we add. And we close. And we add the new analysis case. Finally, we can write the input files and run OpenSees. We're going to look at the gravity case first. And we're going to click run. And we're going to upload. And now we can go click animate response and see what happens under gravity. We can increase the scaling factor to 100 and we can see the deformation. Next, we're going to look at the eigencase. We're going to run and load the eigencase. Now we can check the mode shape. Select the first mode and we'll plot and start to see the animation. Now you can see the second mode and start, and now the third mode, and we see some torsion happening. Finally, we're going to look at the transient case. We write, run, and load the transient case. Now we can see the animated response of the earthquake. Change the scaling factor to 10 and we can start. That's the end of this tutorial. Hope it helps you get a grasp of the 3D building modeling.